Hi, I'm Samir Desai, and in this video I'm going to teach you how to rank the stability of conformational isomers of cycloalkanes.
Cycloalkanes have conformational isomers based on the position of substituents. Now when we draw a cycloalkane, we imagine a cyclic structure that looks like this, with the carbons in gray and the hydrogens in white. For this lesson, I'm purposely drawing a cyclohexane as opposed to any other cycloalkane because this 6-carbon molecule has been extensively studied in organic chemistry and is used as the classic example of a conformational isomer. While we might be used to seeing cyclohexane drawn in a flat hexagonal shape, this isn't a true representation of the molecule. Molecules in real life deal with strains. In fact, in the last lesson, we discussed torsional and steric strains, so the molecule actually looks like this when we view it from the side. Notice the true representation of this molecule is not planar. The most stable conformation is that which minimizes strain, and this conformation has optimal angles between bonds that leads to the least strain. It would be pretty time-consuming to draw 3D structures every time we wanted to show conformations of a cyclohexane. So we have a standard way to draw different conformational isomers of cyclohexanes. This is referred to as a chair structure. The cyclohexane looks like this, and the complicated origins of calling this a chair conformation is because, well, this looks a lot like a chair that my little stick figure human can lounge in. The reason we can have conformational isomers with cycloalkanes is because the substituents can be axial or equatorial. We'll continue working with cyclohexane, C6H12. On our chair conformation, each carbon still has the ability to bond to 2 other atoms or molecules. One will be axial and one equatorial. Any substituent bonded at the blue bonds will be in the axial position. In this case, it would be the 6 hydrogens. Any substituent bonded at the red bonds would be equatorial. Larger substituents will be more stable in equatorial positions that minimize torsional and steric strain. Lastly, cycloalkanes can undergo ring flips to change the position of its substituents from axial to equatorial and vice versa, creating conformers. Ring flips, or chair flips, look like this. Again, we still have a chair structure, but notice the headrest was flipped downwards and becomes the footrest, and the footrest turns into the headrest. Also, keep in mind the substituents switch positions. So the axial hydrogens in blue on the left conformation will now be in the following position on the right conformation. These hydrogens in blue are now equatorial on the right after the ring flip. Similarly, the equatorial hydrogens in red on the left conformation will be axial on the right conformation. Let's use this information to identify the most stable conformation when shown a pair of conformers. Although we are told the following pairs are conformers, let's quickly double check this with A. The pair in A has gone through a ring flip, as we can see the headrest of one chair is the footrest of another. While it looks like the methyl groups are on completely different carbons, keep in mind that when the ring flip occurs, this footrest flips up, which corresponds to this carbon on the headrest, and is moved from the equatorial position on the left conformation to the axial on the right. This is a similar situation for the other methyl group. The most stable conformer has the larger substituents on the equatorial position. Therefore, this conformer, with the methyl groups equatorial, will be more stable. Moving on to B, the bulkiest substituent is here. Again, the largest substituent will be the most stable in the equatorial position. Therefore, in B, the right conformer is more stable since the tert-butyl substituent is in the equatorial position. Lastly, C looks a lot like B, but with a hydroxyl group replacing one of the hydrogens. Now, the tert-butyl is axial on the left, which we know isn't the most stable, but the OH is equatorial, which is more stable. And if the tert-butyl is axial on the left, it must be equatorial on the right, meaning the OH will be axial on the right. So which has more of an impact on stability, the tert-butyl or the hydroxyl group? Recall in the previous video about strain, we talked about bulky substituents having big electron clouds that want to avoid being near one another. Although oxygen is more electronegative, the hydroxyl group is considerably smaller than tert-butyl. Therefore, the position of tert-butyl will influence the stability the most, and the most stable conformer will be the one where tert-butyl is equatorial. The right conformer is more stable. This concludes the lesson on conformational isomers, so hopefully you are now able to recognize these isomers and rank the stability within Newman projections and cycloalkanes.